So yes, let's start. I tried to clean the backboard a bit. So slight recap. So here I've tried to illustrate the trapezoidal rule, and this is supposed to be the Simpson rule. Unfortunately, they ended up looking pretty similar, but this is just a trapezoid, so this is just a straight line here, where we use two interpolating points. So this is just one interval. So the length here is h for this interval. This is the number of intervals. So you are evaluating the function at point f of x0 and f of x1. Whereas for the Simpson rule, depending on how you want to define it, this can be either one or two intervals. It's easier if you just assume that this is one interval. But you need 3 points because you are going to interpolate using 3 points. And then also get a curve like so. It looks straight, but it's supposed to be a curve. Only you have to make sure that the step length is half, because you also have this midpoint of each subinterval, which is important to remember, for instance, at the exam, that this h is different. I mean, there's a reason why it, if you try to illustrate it, you see that, oh, it has to be half of this one, because, well, you have one more point. So the step length is going to be, well, so much more. Also, yes, h b minus a divided by the number of intervals m, and divided by twice the number of intervals, saying that this is one interval here. We can also do something similar as we did for the trapezoidal rule in order to estimate the error for the Simpson rule, but I will just state it, as it's just a lot of work trying to figure it out. But you will see that this is a fourth order method. Instead, CH4 divided by 180. So this is going to be, oops, we need the negative sign as well. So this is the error in the Simpson method. As you can see, this one is of OH2, and this one is of OH4. So this is 2 orders of magnitude more accurate than the trapezoidal rule. We can also list the degree of precision. So this one will have a d of p of 1. Kind of makes sense though, because when you have straight lines, you can only approximate, well, straight lines, which are polynomials of degree 1. Whereas for this, you have a degree of precision equal 3. So you can actually approximate third order polynomials. An easy way to see this is that is basically this h minus 1.
How we get this degree of
Precision?
equal 1 and 3? How we can get it?
Oh, it's basically just the order minus 1.
Okay.
Yeah, order of error minus 1 in these cases. So we'll look at the differences between these in an example. So we are going to be looking at it in kind of reverse and find how many intervals and how many intervals we need in order for a certain precision to be met. So we want the error of f and h to be less than 5 times 10 to the power of minus 9. And then find m and h for T and S rule. For this to be true. So we're going to look at the integral from 2 to 7 of 1 over x dx. So what we need then is the derivative. So we have that f of x is 1 over x, and then the derivative is going to be minus over x squared. Second derivative of x is going to be 2 over x power 4 cubed, and 3 equals minus, is it 6? Yes. Minus 6 over x power 4. And lastly, we need is this fourth derivative of x, which is going to be 24 over x to the power of 5. Well, then we can look at this error term and see what we get. So first, we will, we can figure out the maximum error. So if you look at this, so this is in the trapezoidal rule. The problem here is actually finding this chi, or xi, I guess. It's not really that hard. We are again pessimistic, so we just pick the xi that gives us the highest value. So this one has to be lower than, let's see, the maximum of x into 7 f twice derived of x, and this is then equal to max x to 7 of, twice derived 2 over x power of 3. And what gives the highest value of this? Well, it's the lowest possible value of x we can pick, which is 2. So this will be, 2 over 3 is 1 over 2, 1/4, like so. And in a similar fashion, we can do it with the this mysterious one, and we get that f for xi has to be less than, that's on my row sheet. This has to be less than 3/4. In a similar fashion. So basically we just pick the worst possible number such that we get a, an upper bound of our error. Yep. Looking at this, we see that the ET, so the trapezoidal error, will be, minus B minus A f power of 2 xi over, was it 12? H squared, like so. Well, this is going to be less than 7 minus 2, so b minus a, times this one is going to be less than a fourth, so if we just insert that, then it's going to be less, times h squared divided by 12, and we should be getting, let's go over here, 548 h squared, and we want this to be less than 5 times 10 power of minus 9. Yes? So we could figure out h directly from this, but the number of intervals has to be a integer. Does that make sense? And again, we remember that h equals b minus a over m. In this case, it means that h equals, 5 over m, because 7 minus 2 is, well, 5. So we end up with, let's see, should I do anything? No. That, okay, so the 5s are cancel. We multiply by 48 on both sides, and we get 25 over m squared should be less than 48 times 10 to the power of minus 9, which means that m has to be bigger than or equal to, see, 25 over 48 times minus 9, the square root of this. And this is kind of an unorthodox notation, but you can use this. So you see I don't have anything down here. This basically means round up. You will see it sometimes. It's just a notation. Doesn't really matter that much. But we can solve this, and we'll get that m has to be more than 2, 2, 8, 2, 2. So what shall we pick? Well, we can just pick this number. If we have this amount of intervals, which is 22,822 intervals, well, then we will achieve our degree of accuracy for this function using the trapezoidal method.
This could be 10 power plus 9, isn't it?
Oh, yes, there's going to be a plus here, of course, because we've inverted it. Yep. And then we can use this to calculate the step length. H is then, well, 5 times this 22,822, which is approximately 2.19 times 10 to the power of minus 4. That sounds an awfully lot of work for something so small.
Excuse me.
Mm-hmm.
Why we use x equal 2 in this here maximum?
Here? Because it gives us the maximum value of this.
I mean, we have always get a here. We have to substitute.
Not always. No, not always. So you have to pick, you have to pick the x that gives you the highest function evaluation of this. Since we are dividing by x, the smallest x will give us the highest value. Huh? So if we were to divide by, say, 7 here, what we get a...
Function.
Yeah, depends on the function. So sometimes you can't really pick this. Sometimes your function is very, well, hairy, so you don't really know how to pick it. But, I mean, this is a constructed example, so you can actually pick it. But yeah, the point here is that you need a lot of intervals with the trapezoidal method to get this to work.
Our fx function, x squared,
Mhm.
would be get 7.
Yes, then you would pick 7. Because that's the pessimistic approach. I mean, I usually try to stay positive, but when doing error analysis, it's better to be pessimistic. That's the philosophy of the day. So this is an awful lot of intervals. How does this look with the Simpson rule? Again, we will see the error, ES, is equal to minus B minus A, fourth derivative of f for some xi, then h power of 4 divided by 180. Done with see? This is going to be less than 7 minus 2, 3/4. So why 3/4? Well, that's the highest value this can take. The f chi times h power 4 divided by 180. Like so. Where am I? Yes. And this, we can see, is going to be equal h to the power 4 over 48. And again, this should be lower than or equal to our error, minus 9. And we have the same approach, only that this time we will have that h equals 5 over 2m. So this 2 here. And again, we insert this into this. And now I'll skip some details. If you want, you can do it at home. M to the 4th power should be more than 1, 2, 5, or 7, 6, 8 times 10 to the power of 9. Meaning that M should be more than 2, 5 over 7, 6, 8, and then 1/4 of this. This one is like 113. So we have 113 intervals, which is a lot less than 22,822. So even though the Simpson rule, it looks like you have to do more computations, you are able to escape with less function evaluations. Yes, we can also do h here. So h is going to be, well, 2 orders of magnitude less. So h in this case is 2.21 times 10 to the power of minus 2. So Simpson method is, well, 2 orders of magnitude better. Yeah, I mean, you can just see at the step length here. This is half the step length of what, well, it's just confusing. Anyway, it's, so you see this is 2.21 times 10 to the power of minus 2, whereas for the trapezoidal one, 10 times power of minus 4. So that's a huge difference. Moral of the story, use Simpson's method. A lot better. But then again, why stop there? We can do, again, better. So next we will look at something called Romberg. Romberg, I guess it was a German guy. So Romberg was actually a German guy. He was classified as a, what was the name of it? A half Jew. And he actually was a professor at NTNU. So in the old physics building, they have this huge van der Graaf generator. He helped build it. Problem is, they never used it for experiments. I was supposed to be doing quantum mechanics experiments, but they never started. I guess they ran out of money. This is always a problem in research. Yep. I'm gonna do a cheeky move. Romberg integration. So the idea here, even though as we saw the trapezoidal rule isn't really that good, we will start with it. So the idea and then we want to increase the accuracy. Through extrapolation. To cancel the error terms. Though hearing about it, it sounds very intuitive. So we'll first, start with the trapezoidal rule. And since last lecture it hasn't changed much, this is f of x dx plus t, f and some kind of step length, plus the error term for trapezoidal function, trapezoidal rule. And the interesting bit now is the error term. So it can actually be proven, it can be proven that the error of this trapezoidal rule follows a pattern, which is some kind of constant a1 h power of 2 plus h2 power of, actually 4 plus h3 6 und so weiter, where these AIs are constants. So the goal here is that we can use some kind of extrapolation to actually remove this term. So if you're able to cancel this A1 term, then our accuracy is certainly h to the power of 4. So how do we do this? Well, there are many ways to actually solve this, but we can prove that, well, we have two ways. AB f of x dx. So if we actually double the step length, the h, then we will see we get something like this. T f 2h plus a1 to h power of 2 plus a2 to h power of 4 plus a3 to h power of 6. Whereas solving it with half that step length, we get t f of h plus a1 h squared plus a2 h power of 4 plus a3 h power of 6 und so weiter. Let's see. Like so do you see what we're supposed to do next? What if we just take the 1, multiply it by 4, and subtract it? So this is basically, maybe I can, so if we now just multiply this with 4, so we have 4 of these, we will have 4 of these, 4 of these, 4 of these, and 4 of these. Should be possible. Well, if we take it's going to be like, yes, if we take this one minus this one, this term is going to be cancelled. So we have 4 AB dx minus, well, AB of x dx equals 3 AB of x dx. Yep. Or we could also look at the right hand side, and we will get 4t f of h minus t f 2h minus, well, 0 times a1 h squared minus 12 h2 h4 minus, I think it's going to be 60 a3 h power of 6. So, well, 0. Meaning that our new approximation is going to be doing some algebra. X dx equals 4 t of f h minus t of f 2h divided by 3. And then I'm lazy and I'm going to introduce some more constants. So now we have b1 h power of 4 plus b2 h power of 6 plus something. So you see, by kind of applying the trapezoidal rule twice, we have reduced the error from OH2 to OH4, which is a huge improvement. And then you see, if I do something similar again, I can actually remove the power of 4 and then power of 6, and then it will just become more and more accurate. At the cost of more and more function evaluations, of course, and more intricate math. It can also be proved that I can do this. It can also be proved that this is equal to Simpson's rule. So S of F H. So we started at the trapezoidal rule using Romberg integration. We've certainly ended up with the trapezoidal rule. No, sorry, the Simpson rule. So let's just quickly repeat this. A, B, x, dx. So by just trying to, well, actually just writing this out and just comparing it with the Simpson rule, we see that it's basically the same. H plus, I used B, didn't I? B1 h power of 4 plus B2 h power of 6 plus something. And then again, if we have a new approximation, x dx sf 2h, well, b1 2h power 4 plus b2 h power of 6. And looking at these, we can eliminate everything. Well, not everything, but the h4 term, and we end up with dx equals 16. No, so 16s of h minus s of 2h divided by 15. And then, of course, we have some error, 48 minus 15, b2 h to the power of 6. Something like this. And then you can see there is a pattern to this. And you can continue indefinitely until you've arrived at your wanted accuracy, wanted level of accuracy, or what to call it. Yep. This is okay to remove, or? So, any questions before we continue? Then we'll do the generalized formula. So we have that, well, formula. Well, M1 is going to be 1, M2 is going to be 2, M3 is going to be 4, and so on, which means that Mn is going to be 2n minus 1, giving us h of k equals b minus a over mk, since this is the trapezoidal rule. We'll then have R1, 0. It's going to be h1 over 2 f of the point A plus f of the point B, which is, well, b minus a over 2 f of a minus f of b. This is going to be a plus. So that's the first one. So the 0 here means we're using the trapezoidal rule. Next we'll have a 1, that's the Simpson rule, and then when it's 2, it's a higher, I guess we can call it the order. 2, 0 equals, well, h2 over 2 f a plus f of b minus 2 f a plus h2. So we can rewrite this, and what we get, minus a divided by 4, yes, f of a plus f of plus 2 f a plus b minus a over 2 yes, which by inspection we see that this is 1/2 R1, 0 plus H1 f of a plus H2. Yes. By just rewriting this. And in a similar manner, the next one, 3, 0, skipping a few steps, we get 1/2 R2, 0 plus H2, and then f of a plus H3 plus f of a plus 3H3. So, and then, like working this, we'll see a pattern emerging. So I'm just gonna saving us some time and have the pattern. 1/2 r k minus 1, 0 plus h k minus 1, and then a sum I equals 1 to 2k minus 2 f of a plus 2I minus 1 h k. So that's the for the trapezoidal rule. So you start with this R1, 0, and then you can gradually increase it. So it's a recursive relation. Going on there. I'm just thinking. Yes. So I was thinking I could show you an example of this implementation, but not sure if I have time. So this is for the first, this is just trapezoidal. Hey, we've evaluated at many points, and we can use these points then to get the Simpson rule out of this. So this is going to be RK1, where 1 here means that it's the Simpson rule. RK0 plus RK K0 minus RK minus 1, 0 over 3, k equals 1, 2, and n. Generally, so you can actually expand this further. So I guess this is the last thing I'm going to write. Kj equals R K, oops, j minus 1 plus R K j minus 1 R K minus 1 j minus 1 for j minus 1. So apologies for just rushing through that bit. Do we have like 3 minutes for an implementation? Then we quickly do this. So again, I will try to upload this to Slack, but I see there's a exercise going on this, so I'm not going to upload it instantaneously, but after a while. So what we're trying to do here, we are trying to integrate the sine of x from 0 to pi using 6 so-called nodes. So the nodes are dependent on this k here. So first, this is going to be a matrix, and we are not concerned with memory, so we are just going to store it as an n by n matrix. If you are concerned about memory, then you could store it as a sparse matrix. But here, I haven't bothered. So this is a starting number of kind of intervals, the step length, and then you need to initialize it. So this is the R11. And then you are calculating all these Romberg constants, or, well, numbers, for the trapezoidal rule. And after having done this, you see here, then you can use these from the trapezoidal to calculate the higher order. And the cool part is here that you only use function evaluations for the first column of this R. It might be easier if I just run this and we'll see. So we see using this Romberg integration. By the way, the analytical result here is 2, so we're not quite there yet. But here we have constructed a matrix that looks, can I get this? Like this. Short. Like so. So here you see that the best approximation is always going to be the one in the lower corner here. So you see we don't really gain much in this example. Unfortunately, we can try to increase the number of nodes we're using. Well, we get a better. If we have 20 nodes, this is going to take a while, I guess. And then we have approximated the same. Yes, I will upload this in a while. Yeah. Any questions? Sorry for just rushing through the last bit, but